Good afternoon, GSIS students. This is a third week lecture. Today I'm going to explain numerical descriptive techniques. Last week we learned types of data, enumeral data, ordinal data, nominal data. And also, we learned graphical tabular techniques for nominal data. What was that? Do you remember? Bar chart, pie chart, frequency distribution, relative frequency distribution for nominal data. Then we learned for interval data, we learned histogram. Can you remember? Do you remember? If you don't remember, now it's a good time to check. If you don't know, please check now. Then we learn algebraic. Today, we are going to learn numerical descriptive techniques. Let's see what is numerical descriptive techniques. Glance through what is numerical descriptive techniques. First, we learn measures of central location, mean, median, mode. Then we learn measures of variability, range, variance, standard deviation. Then we are going to learn measures of relative standing, percentile, quartile. I'm going to explain. Then we will talk about measures of linear relation, covariance, and correlation. First, let's see measures of central location. Mean. The arithmetic mean, also known as average, shortened to mean, is the most popular and useful measure of central location. Let's see how it is computed. It is computed by simply adding up all the observations and dividing by the total number of observations. Then we can make this equation. Mean is equal to sum of the observation divided by number of observation. This is mean. Very simple. But as noted, it is the most popular and useful measure of central location. Most popular, useful measure of central location. Let's see location part. When you're referring to the number of observation in population, we use a capital letter, uppercase letter, large N. It is what number of observation in a population. Okay. When referring to number of observation in a sample, we use a lowercase letter n. Arithmetic mean for population is denoted with a Greek letter mu. We read this is a mu. Arithmetic mean for population, mu. Arithmetic mean for sample is denoted with the x bar. Mean, mu, and mean x bar. Mu is for what? Population mean. X bar is a sample mean. Okay? Don't be confused. I'm going to repeat. Population mean is a mu, x bar sample mean. So this is a mathematical notation. Population mean mu. What it is? Sum of observation. Sum of observation divided the number of observation. Mu is related to population. X bar is related to sample. So this is a population mean, this is a sample mean, and you see large n, small n. Okay, sum of the observation. Mu is a population mean, X bar is a sample mean. You should know how to calculate. Now let's see the characteristics of the arithmetic mean. Arithmetic mean is appropriate for describing measurement data. For example, heights of people, marks of student papers, etc. It is seriously affected by extreme values called outliers. As soon as a billionaire moves into neighborhood, the average household income increases beyond what it was previously. Now, let's see another measure of central location, median. Median is calculated by placing all the observations in order. The observation that falls in the middle is median. The median is calculated by placing all the observation in order. The observation that falls in the middle is the median. Let's see this example. 0 to 22. We have this data. Then placing all the observation in order. That means what? Short them bottom to the top and find the middle. Because we have 9 data, this is odd data, then what? Middle is 8. So median is 8. Now let's we have 10 data, then data is 0 to 33. So then bottom to top and middle is the simple average between 8 and 9. Okay. Then median is 8 plus 9 divided by 2, 8.5. That's median. Here we assume 9 data. Here we assume 10 data. Okay, then 8.5, 8. But mean is from previous formula, mean is 7.4, and in this case 10. You know how to calculate mean? Now let's see another measure of central location. In our class, we learn 3 measures of central location: mean, median, mode. The mode of set of observation is the value that occurs most frequently. Mode is the value that occurs most frequently. Mode is useful for all data types, though mainly used for nominal data. Sample and population modes are computed the same way. So in this example, 0 to 33 data, for this data, n equal 10. n equal 10 means what? This is a population data. Which observation appears most often in this case? 0. So mode for this data set is Mean, median, mode, which is best? With the three measures from which to choose, which one should we use? Think about that. Which one should we use? Generally, mean is our first selection. Mean is a first selection. However, there are several circumstances when the median is better. The mode is seldom the best measure of central location, but if our data is nominal data, then generally we use mode. One advantage the median holds is that it is not as sensitive to extreme value as is the mean. That means what? Mean is very sensitive to extreme value, but median is not. To illustrate, consider data in the previous example. The mean was 11 and the median was 8.5. Now suppose that the respondent who reported 33 hours actually reported 133 hours. The mean becomes 21. So 21 is greater than 11. It is much larger than 11 because of this. This value is only exceeded by only 2 of the 10 observations in the sample, making this statistic poor measure of central location. The median stays the same. When there is a relatively small number of extreme observations, it's very small or very large, but not both. The median usually produces a better measure of the central location, the center of data. For ordinal and nominal data, the calculation of the mean is not valid. Ordinal data, nominal data, not valid. Median is appropriate for ordinal data. For nominal data, mode calculation, mode, is useful for determining highest frequency, but not central location. Measures of variability. Now let's move to topics of measures of variability. Measures of central location fail to tell the whole story about distribution. That is, how much are the observations spread out around the mean value. Let's see two sets of class grades shown. This is a distribution over two sets of grades, class grades. Mean is the same in each case. So this is mean 50. Mean is 50. Okay. But the red class, this red one, red class has a greater variability than the blue class. So mean is the same in this case, but the variability is different. Because variability is different, we should measure variability. To measure variability, first one is a range. Range is the simplest measure of variability, calculated as a largest observation minus smallest observation. Range is equal to largest observation minus smallest observation. So for this data set, largest one is 50, smallest is 4. So 50 minus 4, 46. Next one, largest is 50, smallest is 4, 46. As you can see, data is different, but range is the same. So for these two cases, range is the same in both cases, but data set have a very different distribution. From previous slide, we learned how to calculate range. Based on that, let's see what is the characteristic of a range. Its major advantage is the easy with which it can be calculated. Its major shortcoming is its failure to provide information on the dispersion of the observation between two endpoints. Hence, we need a measure of variability that incorporates all the data and not just the two observations. Hence, variance and its relative related measure, standard deviation. Variance and related measure, standard deviation. You will see how it is related. Variance are arguably the most important statistics used to measure variability. They also play vital role in almost all statistical inference procedures. Population variance is denoted by sigma squared. This is read sigma squared, lowercase Greek letter. Population variance. Sample variance denoted by s squared, lowercase s squared. Both of them rho square, sigma square, s square. Variance used to measure variability. And most important thing is this one. Play vital role in almost all statistical inference procedure. Sigma square S. You should know how to calculate. Variance of population is sigma square is equal to summation I equal 1 to n xi minus mu squared divided by population size. So this is a variance of population, and variance of sample s square is equal to summation I equal 1 to, not the large n, the small n, xi minus x bar square. You see here they use a sample mean, here population mean, and here they use a sample mean xi minus x bar square divided by n minus 1. The denominator is sample size minus 1. Not the, here for population variance they use population size large n, right? But for sample variance they use n minus 1. As you can see, you have to calculate the sample mean x bar in order to calculate the sample variance. Alternatively, there is a shortcut formulation to calculate the sample variance directly from the data without the intermediate step of calculating mean. It is given by the following formula. This formula. Let's see example. The following sample consists of the number of jobs 6 students applied for: 17, 15, 23, 7, 9, 30. That's our data, the sample data, right? Because we have a sample here. So this is a sample data. Find its mean and variance. What are we looking to calculate? Following sample consists of a number of jobs 6 students applied. Find its mean and variance. So this is a sample mean, this is a sample variance, as opposed to mu sigma square. What is mu? Population mean mu. This is a population variance sigma square. Let's see calculation of sample mean, calculation of sample variance, calculation of sample variance shortcut method. First, sample mean. X bar is equal to summation I equal 1 to 6 because we have 6 samples. Xi divided by 6 is equal to 17 plus 15 plus 13 divided by 6. So summation of this is equal to here. So 84 divided by 6. So we have a result 14 job. So X bar is equal to 14 job. Sample variance. Because X bar is 14, Xi is 17 to 13. So this summation is 17 minus 14 square, right? Because of this. And 15 minus 14 square. And last one is 13 minus 14 square divided n minus 1. So 6 minus 1 is equal to 33.2. So s square is 33.2. And last one is a shortcut method. Standard deviation. Standard deviation is simply the square root of the variance. Standard deviation is simply square root of the variance. So population standard deviation sigma is equal to positive square root over what? Of the variance sigma square. Sample standard deviation is a square root over s square. Consider example 4.8 where golf club manufacturer has designed a new club and wanted to determine if it is hit more consistently. That is with less variability than with the old club. So which one is more consistent? We can use in Excel data analysis, descriptive statistic. It produces following table for interpretation. And now we are going to focus on standard deviation because current iron is greater than this one and new iron is less than. So you get more consistent distance with the new club. For exercising, we can use data and we can do in the lab exercise session. But now we are in the, our class is online, so just wait, okay? And in the offline meeting, we are going to exercise this example. Now move to topics of measure of relative standing and box plot. Measures of relative standing. Measures of relative standing are designed to provide information about the position of a particular value relative to entire data set. First, we will see percentile. percentile. The pth percentile is the value for which p% are less than the value, and 100 minus p% are greater than that value. Suppose you scored in 60 percentile on the final exam in business statistics class. That means 60% of the other score are below yours, while 40% of score were above yours. Quartile. Quartiles are special name of some percentile. We have a special name for 20 pips, 70 pips, percentile, namely quartile. You should know the name quartile. The first row quartile is labeled Q1. Q1 means 20 pips percentile. Second quartile, Q2, 50th percentile. Q2 is 50th percentile, which is also median, second quartile, median. The third or upper quartile is Q3, is equal to 75th percentile. So third quartile is a Q3, second quartile Q2, first quartile Q1. Q2 is equal to median. Commonly used percentiles. Commonly used percentile. 10th percentile is called the first decile. 25th percentile, first quartile Q1. 50th percentile, second quartile Q2. 75th percentile, third quartile Q3. 90th percentile, 9th decile. This is a commonly used percentile. Note, if your exam mark place you in the 50th percentile, that doesn't mean you scored 80% on the exam. It means that 80% of your peers scored lower than you on the exam. It is about your position relative to the other student. You understand what's the meaning of percentile? Now let's see how to find percentile. First, you have to know what is the location of a percentile. The following formula allows us to approximate the location of any percentile. This is the formula. LP is equal to n plus 1 times P divided by 100, where LP is the location of a pth percentile. LP is n plus 1 times P divided by 100. Let's see example. For this data, 0 to 33, where is the location of 25th percentile? Where is the location? That is, at which point are 25% of the value lower and 75% of the value higher. So L25 is 10 plus 1 times, because this is n plus 1. We have n equal 10. So n plus 1 is 10 plus 1 times 25th percentile, 25 divided by 100. So it is 2.75. So from data, 2.75 is here. Here, you can see here. And the 25th percentile is 3/4 of distance between second, which is 0, 1, 2, first, second, And the third one is 5 observation. So 3/4 of the distance is 0.75 times 5 minus 0 is 3.75. This is 3/4 of a distance between 0 to 5. Because second observation is 0, 25th percentile is 0, 5, 3.75. So 3.75 is second, 25th percentile. 3.75 is 25th percentile. If you don't understand, repeat it again, okay? Then you can understand easily. If you understand the previous example, this slide is very easy. Now let's see. What about the upper quartile? R75. R75 is equal to 10 plus 1 times 75 divided by 100. So 8.25. Let's see which one is 8. One, two, three, 4, 5, 6, 7, 8. This is 8. Okay, 8. 8.25 is around here. Okay. So it is located 1/4 of the distance between 8 and 9th observation. 8 is 14, 9 observation 22 respectively. 1/4 of the distance is 0.25 times 22 minus 14. So 2, which means 75th percentile is 14 plus 2. So it is equal to 16. Please remember. Here, please remember means don't be confused. Position 2.75 means L25, the location over 25th percentile, is equal to what? 3.75. This is a 25th percentile. Right? Okay, so don't be confused. The definition of L25 and 25th percentile. It's different. 16 means what? 75th percentile. Right? Position 8.25 is L75. Okay. So don't be confused the location of percentile itself. LP determines the position in the data set where the percentile value lies, not the value of a percentile itself. It's different. Now we can determine inner quartile range. The quartile can be used to create another measure of variability, the inner quartile range, which is defined as follows. Inner quartile range is equal to Q3 minus Q1. The inner quartile range measures the spread over middle 50% of the observation. So inner quartile range we define Q3 minus Q1, and it measures the spread over middle 50% of the observation. Now let's see box plot. Box plot is a technique that graphs the 5 statistics. What 5 statistics? Minimum, maximum, first quartile, second quartile, third quartile. So this is the location of first quartile, second quartile, third quartile. Generally, this is a minimum, this is a maximum, generally. But in this case, this is a what? 1.5 times Q3 minus Q1. So this size is 1.5 times Q3, Q1. So what? The value of this is Q3 plus this whisker. The value of this is Q3 plus whisker. Okay. To understand that one, you should understand this part. The lines extending to the left and the right are called whiskers. Any point that lies outside the whisker are called outlier. The whiskers extend outward to the smaller of 1.5 times the inner quartile range, or the most extreme point that is not an outlier. If you understand this sentence, then you understand the graph. Generally, minimum, Q1, Q2, Q3, maximum. But new point is greater than whisker. Let's say this is a maximum point. Then your pointer, your box plot, and the whisker. It is 1.5 times Q3 minus Q1. Let's see example. Fast food restaurant. A large number of fast food restaurants with the drive-through windows offer drives and their passenger the advantage of a quick service. To measure how good the service is, an organization called QSR planned a study wherein the amount of time taken by sample of drive-through customers at each of 5 restaurants was recorded. Compare the 5 sets of data using box plot and interpret result. So, to measure how good the service is, we are going to compare 5 sets of data using box plot. This is the result. Popeyes, Wendy's, McDonald's, Hardee's, Jack in the Box. Wendy's service time is as you can see here, this is the measure. As you can see here, Wendy's service time is shortest and least variable. If you understand the meaning of Q1, Q2, Q3, and whisker, largest value, smallest value of the box plot, then you can understand this one. Wendy's service time is shortest and least variable. Hardee's has the greatest variability because this is the Hardee's. Hardee's has the greatest variability, while Jack in the Box has the longest service time. Service time is longest. Okay. So most variability Hardee's. Shortest, least variable Wendy's. Longest service time Jack in the Box. Let's move to linear relationship measure. Linear relationship measure. We now present 3 numerical measures of a linear relationship that provides information as to the strength, direction of a linear relationship between 2 variables. They are the covariance, coefficient of correlation, and coefficient of determination. First example, covariance. Sigma xy is called population covariance. It is this formula. Population mean variable x mu x. Population mean of variable x mu x. Population mean of variable y mu y. So xi minus mu x times yi minus mu y. For this measure, we sum all of them. I1 equal to n and divided by n is a population covariance. Sample covariance, which is Sxy. Summation xi minus x bar times yi minus y bar divided by n minus 1. Okay. So this is a sample covariance. You should know how to calculate. In much the same way, there was a shortcut for calculating sample variance without having to calculate sample mean. There is also a shortcut for calculating sample covariance without having to first calculate the mean. And this is the shortcut to calculate covariance. Consider the following three sets of data. X, Y. You see, for set 1, X267, set 2, 267, set 3, 267. Y is 13, 20, 27, 27, 20, 13, 20, 27, 30. Set 1 data, X increasing, Y increasing. Set 2, X increasing, Y decreasing. Set 3, X increasing, Y increasing, decreasing. So no pattern. Okay? And then you calculate X minus X bar is 5, Y minus Y bar is 20, then multiply, then add this all of them divided by n minus 1, that's 70.5 minus 70.5 minus 3.5. So in this case, X increase, Y increase. That means what? X, Y is the same direction and positively related. Then covariance is 70.5. This case, X increase, Y decrease. And they are related different direction. So covariance is minus 17.5. Weakly or very small relation. So minus 3.5. Okay. And that's what? Interpretation of this one. In each set, the value of X are the same. And the value of Y are the same. The only thing that's changed is the order of Y's. In set 1, as X increases, so does Y. XY is large and positive. In set 2, as X increases, Y decreases. SXY is large and negative. In set 3, as X increases, Y doesn't move in any particular way. SXY is small. When two variables move in the same direction, both increase or both decrease, the covariance will be large positive number, as you see the previous example. When two variables move in opposite direction, the covariance is a large negative number. When there is no particular pattern, the covariance is a small number. However, it is often difficult to determine whether particular covariance is large or small. Coefficient of correlation. Coefficient of correlation is defined as the covariance divided by standard deviation of the variable. So this one, you can read the Greek letter rho. The population coefficient correlation rho is what? Covariance divided by standard deviation x, standard deviation y, and sample coefficient correlation r, covariance divided by standard deviation x, standard deviation y. This coefficient answers the question, how strong is the association between x and y? Characteristic of a coefficient of correlation. The advantage of coefficient of correlation of covariance is that it has fixed range from -1 to 1. If two variables are very strongly positively related, the coefficient value is close to +1. Strong positive linear relationship. That means strong positive linear relationship. If two variables are very strongly negatively related, the coefficient value is close to -1. Strong negative linear relationship. No straight line relationship is indicated by coefficient close to 0. That's how to interpret coefficient of correlation value. More explanation of coefficient of correlation. Rho or R, strong positive linear relation for this case is close to +1. And the graph is like this: x, y, and it's close to +1, that they should similar to this graph. Low relationship is a coefficient of correlation value is close to 0, then the graph is like this. Strong negative linear relationship, in this case, coefficient of correlation value is -1, close to -1, and their graph similar to this. Let's see example. Calculate coefficient of correlation for 3 sets of data. For this data set, we already calculate covariance. Based on covariance, we calculate coefficient of correlation. Because we have already calculated covariance, we only need to compute standard deviation over x and y. To calculate standard deviation over x and y, we calculate the mean x, mean y, and x square 7.0, xy square 49. Then standard deviation as x is 2.65, as y is 7. Then coefficient correlations are as follows. For set 1, covariance 70.5 divided by 2.65 sy 7.0, then what? Close to 1, 0.943. Strong positive relationship between x and y. Set 2, minus 70.5, 2.65, 7. So strong negative relationship. Set 3, close to 0. So no relationship. So up to now, we learn numerical technique for descriptive statistics. And for population, we use large n, sample small n, population mean mu, sample mean x bar, sample population variance sigma square, sample variance s square, population standard deviation sigma, sample standard deviation s, and covariance rho, sample covariance sxy, population coefficient correlation sigma xy, sample correlation r. So you should know all of this. You should understand and their characteristic. For numerical descriptive statistics, we learn measures of central location, mean, median, mode. For measures of variability, we learn range, variance, standard deviation. For measure of a relative standing, we learn percentile, quartile, measures of linear relationship, covariance, correlation. And you should know how to calculate and their characteristic. For next topic, we will learn a little bit more difficult than this one. Okay, see you in the next topic.